Okay, great. So for our second talk today, it's our pleasure to have Edward Varvak from UIC, who will be talking about the Monodromy of Lagrangian Fibrations.
Thank you for inviting me, for giving me this opportunity. I want to talk a little bit about how one can use Hodge theory to attack just fairly classical questions about algebraic geometry. So I guess let's start with a theorem. This is due to Voisin and Bogomolov. So the theorem is if X is a connected compact Kähler manifold, if the canonical bundle of X is trivial, then X is isogenous to, so isomorphic to like finite data, to the following product. I'm going to have an A here. I'm going to have a bunch of Xi's. And I'm going to have a bunch of Yj's. Okay, where the components in this product. So this guy is the most straightforward. A here is a complex torus. So in particular, if this compact Kähler manifold was a projective manifold, then this would be an abelian vector. These are going to be what we call hyperkahler. Talk about them in a minute. And these are strict Calabi-Yau's. Okay, I won't say too much about what the components here are, besides complex tori are fairly well studied. We'll see them in today's talk. These Calabi-Yau's are a more recent notion. They came up due to like physicists in the 90s that found a lot of connections between string theory and geometry. And they're not as well studied as complex tori, but a lot is known about them, especially due to recent work of Laza and Friedman. And hyperkahlers are a little more mysterious. Not so much is known about them. There's not too many examples. And really, so they're sort of the topic of today's talk. There are ways in which we can get at these. So let's find them. Again, connected, compact, Kähler manifold. X is hyperkahler. If it's simply connected, so no torus factors as up there, and crucially, it has a unique holomorphic symplectic form, which I'm going to write in the following way using sheaf cohomology. Take wedge 2 of the cotangent bundle. And I want this to be a global holomorphic symplectic form where sigma is non-degenerate everywhere. Okay. So a few remarks just based on the definition. yeah, the first thing you're going to want to notice is, okay, so X admits a symplectic form, which automatically just means that the dimension of X is even. So complex dimension of X is even. Okay, more importantly, there is a natural map from the tangent bundle of X to the cotangent bundle of X, where if I have a tangent vector field, I can contract it. I can consider the associated contraction with sigma. And the condition that sigma is non-degenerate is the condition that this is an isomorphism. Okay, so in particular, tangent bundle and cotangent bundle of one of these are always isomorphic. Okay, so let's do an example. So the best examples of these are K3 surfaces. So let's remind ourselves that these are, well, the easiest example of a K3 is if I just take a plane, like a quartic surface inside of P3, say x to the fourth plus y to the fourth plus z to the fourth plus w to the fourth equals 0. That cuts out some surface in P3. Okay, it's simply connected by hard Lefschetz. And you can check by adjunction that the canonical bundle of S is trivial. So in particular, it is hyperkahler. Okay, the other prototypic example is you can take the Hilbert scheme of points, Hilbert scheme of n points on a K3 surface. I'm going to denote it by S bracket n. And one can check that it inherits a non-degenerate holomorphic symplectic form on it. And one can check that it is also K-trivial. And in fact, it is simply connected and thus a hyperkahler. Okay. So, any questions on that? Okay, so how to get at these? Well, here's one potential avenue. I've given you a symplectic form, so maybe let's use it. Okay, so a proper map. Let's say F from X to B. Let's say proper surjective map. Where, okay, I want B to not be trivial. So let's have the dimension of B be somewhere between 0 and the dimension of X, which I'll have be 2n. Okay, so a proper map of this type is a Lagrangian fibration. If the fibers are Lagrangian. I'll say what I mean by that in a minute. Okay, so this is a condition on the symplectic form. What I'm saying is, okay, so if I take a fiber and I restrict my symplectic form to that fiber, I want it to vanish. Okay, this is what it means to be isotropic, but I need more than that. I want it to be maximally isotropic. So I want the dimension of all the fibers to be half of the dimension of X. Okay. So this is what it means for a proper surjective map to be a Lagrangian fibration. Kind of a restrictive.
This fixes the dimension of B.
So
Yeah.
why did you give a range of dimensions for B?
Well, it'll become clear in a minute. In fact, we don't need to assume very much about B. As long as such a map like this exists, that B has dimension in this range, it's automatically forced to be a Lagrangian vibration. Yes, sorry. It was a little sloppy here.
So B will have dimension n, or am I?
Yes, yes, B will have dimension, yeah. But a priori, it's not clear that B has to have dimension n if it's not a Lagrangian vibration. Just any proper surjective map could exist unless you know that such a proper surjective map has to be a Lagrangian vibration. Yeah. Yeah, so okay, so here's the, yeah.
So the first part of the definition is for vibration. The theorem is that
Yes.
for a hyperkahler, any vibration is a Lagrangian vibration.
Oh,
Yes, sorry. Here, let me just state the theorem. This is due to Matsushita. Yeah, so a vibration B. So yeah, so let F be a vibration like this. Then yes, first of all, F is a Lagrangian vibration. Okay, secondly, so as you said, the dimension of B is n. Moreover, B is a projective variety. Whereas a priori it could have just been any analytic variety, any normal analytic variety. And thirdly, and probably most importantly, the smooth fibers are abelian varieties. Okay.
sorry, so to be Lagrangian vibration, your fibers have to be smooth, or if not, you just mean they're generically Lagrangians on the smooth
No,
lines?
all the fibers should be Lagrangian, even the singular ones.
What does it mean for a singular fiber to be Lagrangian, a singular point?
I guess,
Just the smooth part is Lagrangian.
yeah, the smooth part of the
This is
singular
what-
fiber.
Reduced fiber.
Oh, they're even reduced, that doesn't have to be.
Okay. So, yeah, so how to study vibrations. Right, so if I hand you a vibration, I guess let's just take the smooth fibers for simplicity so that it's an actual vibration. The smooth fibers of Lagrangian vibration. So there's a few things you can study. So first of all, you should understand the fibers. You should try to understand the base. And the third thing is you want to understand sort of how the base acts on the fibers. So specifically, how does the fundamental group of the base act on the fiber? Okay, and I will explain what is known about the first and second bullet, and then I will tell you how we can study the action of the monodromy on the fibers.
Sorry, what do you mean by the action of the monodromy?
Yeah, I should be, okay, so if the vibration, or if this is an abelian variety, then in particular, it can, I mean, it's identified with its weight one Hodge structure. And so there's an action of pi one of the base on the weight one Hodge structure, just coming from the local system underlying the variation of Hodge structures. And so that's what we want to be studying.
It would like preserve the Hodge structure, right? Just the X on the monodromy.
Yeah, well, yes, yeah.
Maybe he's saying you want like an H1 of it. Or whatever.
Okay, so, yeah, so let's maybe talk about the base a little bit. So this is also due to Matsushita. Okay, maybe, yes, this is a more recent result. But the point is, the base of a Lagrangian fibration has, okay, put this in quotes and I'll explain in a second, it has the same numerics as projective space. So what I mean by that is, okay, so for example, projective space is Fano, so B, okay, B might be singular, but it is Q Fano, which means its canonical divisor is Q ample. Also, okay, so projective space has Picard rank 1. B also has Picard rank 1. And well, projective space has very nice cohomology where it's all just the middle cohomology is 1 in degrees, in even degrees. And B has the same cohomology where they really should take intersection cohomology because it could be singular. But the point is the cohomologies agree. Okay, so, and in fact, there was a big conjecture of Matsushita that just every single base of a Lagrangian fibration should just be projective space. Not much that's known. I mean, it's known in dimensions 1 and 2 for the base. I don't think any dimensions higher are known entirely, but there is this celebrated theorem of Huang. Is if B is smooth, then B is isomorphic to projective space. Okay, any questions on that? All right, in that case, let's talk a little bit.
Conjecture of Matsushita, it's just that B is smooth.
Sorry, what?
You said the conjecture of Matsushita was that
Yeah,
so the conjecture reduced to.
yeah, it would be enough to show that B is, that would suffice. I don't know if at the time that he conjectured it, it would have been enough, but certainly now it is. Yeah, okay. So, let's talk a little bit about the actual fibration. Okay, so, let's, V be, okay, I'm gonna want V to be the variation of Hodge structures underlying just the push forward of the constant sheaf Z. So this is just fiber-wise, this is the H1 of the abelian fibers. Okay? So here's this is a theorem. Okay, so the original theorem for a very general Lagrangian fibration was due to Van Diemen and Voisin. And then in full generality for every Lagrangian fibration due to Ben is that, okay, the period map associated to this variation of Hodge structures is generically immersive. Or trivial. So there's sort of no in between. Either the fibration is isotrivial, all the fibers are isomorphic, and the period map is just the map to a point, or the vibration varies maximally. There's no like fixed parts, nothing like that. Okay. And so another theorem about this variation of Hodge structures. So Voisin proves, yeah, this is due to that. So she proves that, okay, so if I take what I'm going to call VR, which is I take the variation, tensor it with R, so that's a real variation of Hodge structures, and the claim is it is irreducible as an R variation. Okay, so here is the theorem we'd like to talk about today. This somewhat generalizes her result. Okay, so take this variation V. This time tensor it all the way up to C. And so I claim that this complex variation of Hodge structures is irreducible. And I claim, moreover, it's not just irreducible as a complex variation, it's also irreducible as a complex local system, provided that the fibration is not isotrivial. Okay, is that very reflective of the statements? Right. Okay, I'll say a few words as to the proof. Okay, so the idea is this. So let's take this VR that Voisin proved was irreducible as a real variation of Hodge structures. Okay, let's tensor it up to C. Now, by Deline, this just as a complex local system, this is actually semi-simple. It's semi-simple as a complex local system because it comes from a Z variation of Hodge structures. I mean, there's more general results due to Simpson that you can do this for things that even don't come up as Z variations, but for our purposes, this should be enough. And moreover, he proves that the UIs can be almost uniquely equipped with the structure of a complex CVHS. Okay, so here's what we're going to do. Let's have U be an irreducible factor of V over the complex numbers. Okay, so if U is just equal to V on the nose, we are done. Otherwise, here's something we can do. We can take U and add it to its complex conjugate, And we can make sense of complex conjugation because V came from a real variation. So it's endowed with a natural way of complex conjugating. Okay, so this is some subvariation. Sorry, this is a priori just a sublocal system of V. But these both have a structure of a variation, so it's a subvariation. And in fact, okay, this is self-conjugate, so it's defined over R as a local system. We call the underlying real local system W. And the point is this. So W can also be equipped with a structure of a variation of Hodge structures, a variation of real Hodge structures. So all of a sudden, I have an inclusion of real variations of Hodge structures, W into V. But Voisin proved that V is irreducible. So we have equality on the nose. And so we see that there's really only one possibility for what V can be if it's not irreducible. It had better be a product of something and its complex conjugate. Okay. All right, and well now the key ingredient in the proof is this theorem, beautiful theorem of Ben and Christian Schnell. Okay, so the theorem is, remember we had this contraction isomorphism between the tangent bundle and the cotangent bundle. Well, actually, so they both sit in these short exact sequences where, okay, I have the tangent bundle of the base here. Similarly, okay, this is the cotangent bundle of X. Okay, this is contravariant, so this should be the relative cotangent bundle. Okay, and the claim is that contraction actually gives an isomorphism between the tangent bundle of the base and the relative cotangent bundle of X over B. Okay, well, this is identified by definition with F1 of our variation, the top piece of the Hodge filtration. Okay, this is not their theorem, by the way. This is just, you can see this by observation. But what they prove is that this actually extends, right? Here we took the smooth part of, sorry, we took the part of V where the fibers were smooth. But actually, we can extend this to an isomorphism of just all the smooth points of V. We have the tangent bundle there, maps isomorphically to, okay, I'm going to write something down here. I won't tell you what it is. F1 V bar, this is Deligne's canonical extension of V with residue eigenvalues in the interval from -1 to 0. But the point is, it's just some bundle that plays nicely with the Hodge theory of V. Okay, now we have assumed that V splits into two Hodge structures, U and U bar. So in particular, the F1 piece splits into an F1U and an F1U bar. And so the tangent bundle of B splits into a direct sum of two subbundles. Okay, well, in the conjectural case where B is projective space, we're just done. Tangent bundle of projective space does not split. Okay, in the other cases, a little bit more work has to be put in. I'm quite over time, so I will just say it in 30 seconds. What has to happen? So
in 5 minutes lit, so I think we can give you a couple minutes.
Okay. Well, I wasn't going to get through it anyway, but it shouldn't be. Yeah. So the idea is this, right? Remember, I said that this is a theorem of Matsushita that the base of a Lagrangian fibration at least has the same numerics as projective space. So in particular, you would want that the H1 of the base, the H1 of the sheaf of reflexive differentials, you would want this to be even. You would want this to be odd. In fact, you'd want it to be just 1, as it is in the case of projective space. There's something here I'm sweeping under the rug. You need to know that this like computes the Hodge structure on the base. That's also a theorem of Ben and Len. But the point is, we know this can't happen because, okay, this is just the dual of the tangent bundle. The tangent bundle splits. So this had better be even, whatever it is. It's not going to be C. Okay, so that rules out the case where U is self-conjugate. So it can't be a squared, at least. Okay. So what to do when it's not self-conjugate? So U is not isomorphic to U bar. What we do is, okay, at the very least, we know the tangent bundle of B admits some kind of splitting into what I'll call E1 and E2. And what we show is that one of the pieces, say E1, admits an algebraically integrable subfoliation. Okay, I mean, the idea here is this. Right, E1 is a foliation. Okay, this is also a theorem of Ben with Schnell in the same paper. Things that come from Hodge theory form foliations in this way. And we find actually a subfoliation. And so the point is, moving along this subfoliation of E1 actually fixes E2. Okay, so the idea is this. We basically give the base almost the structure of a fibration. There's some caveats here you have to be a little bit careful about. But then what we can do is, okay, so we can take the variation, we can push it forward to this leaf space, we can pull it back, and that has to sit inside of our variation. And I mean, this comes from geometry, so in particular, it's defined over Q. But V is irreducible as a variation of Hodge structures over R even. So this just has to be the whole thing. And so V can't possibly vary maximally. That gives us a contradiction. All right. Yeah. Thank you for your time.
What's this?
User, if B is Pn, Pn doesn't map to D mod gamma, right? So what happened there?
Well, you're mapping all of PN, right? You're just mapping the smooth fibers.
But conjecturally, B is,
B is smooth. All the points of B are smooth.
oh,
But there's a discriminant, certainly.
I see. Okay, I understand.
Yeah, the degeneracy law.
Right, I understood what you were saying. Yeah, that makes perfect sense.
Other questions? Okay, let's think it.